Yeah, so you heard already about the smart city application that we sort of are using as part of streetscapes. Jorge talked about it, and you know, of course, you heard about Cosmos. So there are a couple of slides here. I'll skip through them just in the interest of time, and it's been a long day. So you know, it's sort of the whole idea is to sort of look at this concept of smart intersection and try to figure out what's going on. And you know, you heard all these noble ideas of helping people and trying to figure out what's going on, but the actual thing that we try to do is sort of take the sort of look at the situational awareness and see how we can try to figure out what's really going on. And you will see some examples of what we try to do by looking at where we can position cameras and how we can sort of look into the situation while at the same time trying to preserve privacy. And that's actually one of the things that predates the streetscapes that we are talking about. And it was sort of done as a tangential thing to the Cosmos deployment. And just the fact that we were able to deploy things on the corners of the interesting place like West Harlem gave us an opportunity to play with things, right? And this is the outcome. So, of course, the focus is on safety, right? So in that sense, we are looking at sort of the typical Cosmos thing, right? And we are talking about crazy place like New York City, right? And the idea is that, you know, we are talking about, well, I'm not sure why this is not progressing. Let me see if this is going to work. And it's not. So, no. Okay, there it comes. So the whole idea is that you need we are hoping that by using the side sensors or roadside sensors, we can improve the situational awareness. In other words, the individual cars, what they can observe is not enough to improve safety. And of course, this is sort of, we witness this every day, more or less, in what the people are reporting, that, you know, pretty much all the self-driving implementations that we know of today are limited to whatever the car is observing. And clearly, we are seeing that the rate of accidents is more or less similar to what human drivers are experiencing, right? Therefore, we are not improving safety by doing self-driving. I mean, maybe at some point in the future that will improve on its own, but you know, the assumption is that if we can add additional sensory observation by the infrastructure, we can actually improve. And you will actually see that that's true. And then, of course, in a place like New York City, pedestrians are unruly. I mean, they do things that you don't expect them to do. And my favorite is actually somebody mentioned it today. The biggest problem with the self-driving cars is that if you have a pedestrian who is wearing a stop sign on their back, or bicyclist, and that's actually one situation. Somebody actually had that, where the guy was actually wearing a stop sign on his back and was driving a bicycle. So can you imagine? I mean, what is the car behind you going to do in that situation, right? Which, of course, human drivers can handle that pretty well, but you know, I'm not sure a self-driving car would know what to do in that case. Anyway, right? So, you know, of course, the whole idea is, I mean, this is the Cosmos deployment, right? And in our case, the focus is really on a very specific site, and this is the intersection of Amsterdam Avenue and 120th Street. And we have actually 4 cameras there. Unfortunately, they're not deployed the way it's shown here. We actually have 2 cameras that are sort of low-angle street-level cameras, meaning that they are at about 12 to 20 feet above the ground, sort of looking into the intersection. And then we have what we call the bird's view cameras, which are at 12th and 14th floor, 4th and 12th floor, sort of observing the intersection from the above. And there are various reasons why they're deployed the way they're deployed. But the whole idea is to sort of try to look into how this different positioning will enable us to do situational awareness from the intersection perspective. So in other words, now we are not looking at what the car observes, but what the infrastructure can observe about what's going on. right? So, and I'm just and then of course, given that it's Cosmos, right, we have a lot of infrastructure behind it, behind all these cameras, both near the cameras and far away from the cameras. And we can play, as you've seen, we can play with how we create topologies, processing topologies. We have a lot of GPUs, FPGAs, and can do all sorts of crazy stuff in terms of processing. So now, bird's eye view, right? So, and you can actually see that this is heavily processed view, right? So if you think about it, bird's eye view doesn't give you this. This is heavily processed. In other words, the whole picture was, or whole video was actually turned into 90 degrees view. You don't get that without heavy processing, right? So you have to sort of do a lot of orthogonalization of the view. And then, of course, a lot of YOLO processing, what we call the YOLO processing, to sort of do the object detection, right? And then, of course, tracking, because we're talking about video, right? So you want to track objects as things are happening. And then the beauty of the bird's eye view is that this is sort of privacy preserving, because things are too far away and too small for you to be able to identify. And you will see later on in the presentation, the things that we are concerned about are faces and license plates, right? Because that's what can uniquely identify people. Now, there are other issues. You know, I can easily identify people by what they're wearing, and you know, you can show that there are. It's not enough just to do faces and license plates, but let's put that aside for a moment, right? So we are just primarily concerned with faces and license plates. Sure.
A very good question. You said because in video we want to do tracking, right?
Yes.
Is the application required tracking? Because I assume the tracking is just in the field of view that you're showing here, right?
Yes.
In other words, I see the detection, right? That you do.
Yes.
But is there any value to do tracking just within the field of view?
You will see now what's happening afterwards. Because remember, this is the intersection. And so the idea is now, and actually there will be a later on a slide that actually the video that shows you the value of tracking and why it's important. But you know, the assumption here is that tracking will help us avoid problems that can result from sort of pedestrians colliding with cars or cars colliding with pedestrians, whichever way you want to. I mean, assumption is that two pedestrians colliding with themselves is not important, even though that is actually one of the objectives later on, not in the sense of killing each other when two pedestrians here, but with COVID, right? I mean, that also has maybe deadly consequences as well, right? So anyway, the tracking has its applications, and you will shortly see it. And in this case, you can see that actually we can track, right, quite successfly, both pedestrians and vehicles, and maybe even the sort of disambiguate who's who and what's what, right? So now there is the sort of the whole idea is this sort of problem of how fast you can do things, and of course how accurate you can do things. And this especially is true for tracking, right? Somewhat easier is detection. Tracking gets a little bit tricky because things are moving, you lose who's who, you will lose the trajectory, and then very quickly you start doing crazy things, especially if you're trying to figure out the trajectories of things. So I'm not going to bother you with numbers. I mean, there are some, and these, as I said, these slides will be available later on. But you know, you can actually see that, of course, it strongly depends on the resolution and the size of frames that you're using. But the ultimate thing is that, you know, you can actually get fairly decent performance with the very basic stuff, right? And as you can see, if you lower the resolution or, you know, scale of the video, you can actually get to really high frame rates. And if you use FPGAs, you can push that even to sort of hundreds of frames per second in terms of processing capability, right? So, and of course, the accuracy, you know, you're always trading the accuracy with the resolution as well. So, you know, there's a lot of optimization one can do, trying to figure out what's the resolution and how much accuracy you're willing to sacrifice in order to get information in time. And again, you will see at the very last slide why, and I think Jorge also mentioned this, why is it important for us to get the latency down and to sort of respond in time to certain events that are happening in intersection. Now, you were asking, why do I want to track? So the idea is to sort of have a radar map, right? And of course, it's sort of the whole idea of radar map is to detect things in real time and to predict what's going to happen. I mean, of course, prediction is let's put that aside a little bit. But if you just look at something like this, and I hope the animation is going to start. It's always an issue with these slides, right? So you can actually see here, the radar map is actually something that we are after, right? So if you look at that tracking, and it's actually, of course, it's slowed down. The idea is that you're getting these trajectories and these vectors sort of pointing out the speeds in both pedestrians and vehicles. And the assumption is that now we can do really prediction of whether pedestrian trajectory and a vehicle trajectory are going to intersect in a way that's not good, right? Now, of course, what do we do with this? It's one thing, and this is actually something that's related to, and I'm always using this as an example of age of information, right? It's quite bad if I tell you 5 seconds after you're hit with the car that you're about to be hit by a car, right? So the idea is that, we want to sort of broadcast these maps to everybody and sort of tell them, hey, try to figure out if you are the one who is in a dangerous position and you're going to be hit by a car, or maybe do some sort of heavy processing on the central site to see who is in the dangerous position and try to warn them somehow. Now, how do you warn them? I have no idea. That's, to me, this sort of actuation part is a big mystery. How do we tell a particular person or a particular driver that, they're going to do something bad, right? That's from the situational awareness point of view. So that's why we are sort of...
Send me, I'll probably do something bad.
No, that's not that. Yeah, right. No, but I mean, that's the idea. So if you broadcast this to everybody, maybe there is some mechanism by which everybody can filter it out and yes, sir. I don't know. So yeah, I'm sure we can involve NSA and try to get to correlate something and figure. I mean, I'm joking, of course, but
broadcast an alert to everybody on that.
That's the whole, yeah. So at the moment, the idea is we are broadcasting this, right? So the idea is we are broadcasting the radar map, and hopefully there will be some sort of an application where people can figure.
An alert, like we get on the weather.
Absolutely. So there are all sorts of, and this is actually something that in smart streetscapes we are actively going to sort of look into and try to figure out what are the mechanisms by which you can actually figure this out, whether the phone itself figures out, oh, this applies to me, or somehow the system sort of targets the particular device. I mean, there are all sorts of ideas floating around, but it's definitely a non-trivial problem and something that needs to be, we can do a lot of predictions, but it's not clear how we can actuate or inform whoever. And actually it gets even more interesting if we say detect the person who is crossing the crossing is say a blind person, and we really want to make sure that nobody does something bad to them.
The value add is tremendously with the video. There's a lot of the safety distractions that I don't know with the radio quality, but it seems that adding the video component.
Absolutely. Right. And with cars, maybe we can start broadcasting heads on, of course, assuming that heads on is not something that will distract you, but just isolate some portion of the relevant portion of what.
Let's back to what we know this. Did you see any benefits of using radar?
Well, so that's actually what's not shown here is that what we are now doing is not just using these sort of radar maps, but also using something that we did in a different project, and I don't have slides on that, where you can actually get a point cloud out of the intersection that actually either based on LiDAR or radar or whatever other sensory information you have to create three-dimensional spatial situational awareness.
Dismissive of using radio means to sense?
No, not at all. As a matter of fact, the whole idea is to integrate all of this. Now, of course, the computational complexity of something like that is a separate story. But
You're not saying video and nothing.
No, on contrary. We are talking about all of these being fused into a uniform picture of some kind. I mean, I don't want to call it picture. It's wrong. It's
Has
some.
to be an alert.
Well, so radar does. So again, the question is, when you say radar, LiDAR is a form of radar, right? But except gives you.
Let's say 28 gigahertz.
Sure. So you have, but how do you integrate? So think in terms of if each car is sending that up, right? You have to fuse that in terms of where is that car aimed, and it's yes. The answer is yes, but you have to integrate all that information and figure out what's going on.
Why is the radar?
No, that's a vector, right? So think in terms of the length of the vector is corresponding to the speed, and it's just a representation. That's we are calling it radar. It's not. It's a equivalent representation of the vectors of the car motion, right? It's not radar. We call it radar map. It's nothing to do with radar, right? So yeah, this stops this. Okay, finally. So as I talk, we are also at the same time trying to sort of make these recordings and stuff available to everybody. But in order to do that, we need to do all sorts of blurring and stuff, right? So, and of course, these are flipped. I just noticed that it's sort of license and coordinates head is being represented as anyway. Doesn't really matter. The whole idea is we need to blur faces, and so this is the pipeline that we have. And hopefully we'll get to a point where we can actually have this live, meaning that we can open these feeds. But as said, there is all sorts of technical issues where you do have misses, and quite often you start seeing people's faces in certain situations. And given that we are governed by IRBs, these guys, IRB stands for Institutional Review Board, which is sort of guys who control what we do and make sure we don't reveal personal information to people while doing research, right? So they are after us, and they want us to make sure that we don't do these things. So we have to sort of show them that we are somewhere on the side of these curves where we don't reveal accidentally faces and license plates, right? Which means that we have to actually show them that we don't reveal in a single frame or multiple frames either a license plate that can then be read or a face of person. Right, and then you have a lot of edge cases, as we discussed, right? When people sort of move in front of objects, you can start seeing sort of where you see that blurring algorithm misses the face and stuff like that. And of course, this means just that there is more work need to be done. But anyway, there is a real time sort of or something that we are trying to do real time to get the feeds available for everybody to use during the now. This is just a sort of now applications of this, right? So talking about standard stuff, right? One of the things that we did in the past is sort of look at the counting, and this is the traditional traffic planning type of thing, right? Once you have these radar maps, in addition to using the for safety applications, you can of course do all sorts of city planning stuff where you see how many vehicles are turning left, right? Do you need to expand the lane? Do you need to, and this is traffic engineering. I mean, civil engineering stuff that I shouldn't talk about because I don't know much about it, but we can certainly feed them historical and all sorts of data. And we did actually a project where we are feeding one of the European startups that is doing historical traffic analysis. We are feeding them these anonymized data feeds with the speeds and traffic counts from these intersections, and they're doing quite a lot of traffic planning using these things. Okay, now, another thing that we did, and I was jokingly talking about pedestrians hitting each other, is the social distancing. And of course, this was interesting during the COVID, right? Same way we are doing this with cars, you can do it for all sorts of other things. And then, oops, sorry, this is the video that I wanted to show. So I need to do this, right? So once you calibrate all these cameras and can do things, you can sort of say, okay, I can put the sort of a perimeter area around each pedestrian and see when they're encroaching on each other's circle, right? And you can actually see here when they are violating the social distancing rules, right? So, I don't want to give Big Brother impression here, right? But what's interesting is, not that you want to use this to chase people afterwards, but what's interesting is that you can do all these sort of analysis and sort of figure out what was happening and why it's happening. And I'm sure that there are a lot of epidemiologists that would love to see these things sort of done on a regular basis to sort of see how the epidemic spreads in the city, maybe not for COVID, but the flu or any other disease, right? And so, of course, there is also the processing flow that sits behind that. And, of course, the idea is to do all this in real time and have this available all the time. I just want to make sure that nobody here thinks of Big Brother. We don't do that stuff, right? This is just research, okay? So,
You got any muggings on your
well, that's actually one of the worries, right? I mean, you could record all sorts of things, right? So it's not, we really have to worry about that stuff as well, right? So, I'm not sure I want to have to deal with that stuff ever, right? But chances are we'll have to, because, those cameras are out there, they're recording. If it happens.
So they do it like 24/7?
No, we don't record. I mean, it's experimenter chooses when they want to record, right? So, but access to the camera is somewhat controlled because it's governed by the IRB. So, you have to register an experiment first, and we have to have an IRB for that particular experiment in order for. So there is a preparation for that needs to go there.
I was going to ask you, you said you schedule the time. Have you done anything at night?
Yeah. So it's. I mean, we have it. Nights. They're not IR, but there is enough street light that you can get enough information. I mean, you probably cannot see the faces and license plates, but for most of the stuff you can get good enough. And these are 4K cameras, right? So at least the lower ones are 4K, so you can. I mean, you get good enough outcome from them, right? So, and then this is the last slide, right? So, the real-time stuff, right? So the whole idea, and this is our favorite slide, right? So you can really easily scale everything by the speed of vehicle. And it's all about how fast the cars are going in New York City. And, you translate that into what the cameras are doing. And you're sort of talking about what you do in one frame is approximately, right, 0.1 meter, right? So is that enough to prevent an accident? I don't know, but that's at very low speed, right? So I don't know of any vehicle in New York City that drives at 6 miles an hour, right? Or 10 kilometers an hour. I mean, it's more likely 50, right? Or 30, which means that, these distances are much more serious, right? So that sort of shows you. And then, of course, we always jokingly say that, MPEG cameras have 10 frames, which is 300 milliseconds latency to start with, right? So I don't know. We are talking about 5G, 1 millisecond, and then you have a camera that has 300 milliseconds. So forget about all the stuff that we are doing to speed it up when you have that. And 300 milliseconds at 30 miles an hour, by the time we tell them that they're going to be hit, it's there on the floor, right? Okay, so that's it. This is sort of the last slide, and so I'll take any questions and stop here.
All right, thank you. And you've been having questions. Okay.
Yeah. So we can talk. Yeah, so the lower you go, the accuracy drops, right? So,
Affecting actually the people who are actually going to get killed.
Well, so that's well, maybe yes. Yes, it's a trade-off, right? So you can argue, or I mean, I don't know, right? So
I guess the question is, what residue do you really need? Like the salt children and the salt.
Absolutely, yes, absolutely. Same as LiDAR. How far do you need, or radar? How far does your radar need to go? Right? I mean, it's all these sensory inputs. How accurate they need to be for you to, right? Right.
Maybe you saw what was the compute you needed to?
Oh, so all these are done with a fairly serious compute engines behind them, right? And it's sort of, it's these are big multi-core, like 12 or 24 core machines with A100 GPUs. And, we are actually thinking about moving to FPGAs because it's, that buys you, right? If GPU can do 30 frames per second, the FPGA can do 100, right? YOLO detection.
The cameras are backhaul, right?
Yeah. Cameras use, yep.
So let's say you go about building such as one city or a cityscape. Are you planning to come up with estimates of how much extra data you will generate and shuffle through the wireless and how much power you need?
So that's a crazy amount, right? So even if you think just the Cosmos, which has a relatively small footprint, we don't have enough computing power to do all of this real time with all the cameras that we have.
Yeah. So, but it's a question of compute and
communicate
resources.
Yeah. So communicate, we are actually on the edge of being okay, but compute is nowhere near, right? Because you essentially you need one big server and one big GPU per camera, per task, right? Think in terms of if you say, and then this assumes that you're not doing any serious fusion about multiple sensors, right? If you sort of say, oh, I'm not going to fuse 3 cameras and the LiDAR and the sensor, and the car is not going to send any data that you're going to try to coordinate with in time.
You try to estimate how much you would need to pay to Amazon?
No, but that's a, yes, that's
how
a,
much each wireless capacity, how much
yes,
each,
so it's
capacity,
yes.
how much
And remember, the only reason why we can do this is because we have our own fiber. So we have a full fiber footprint with 100G or 200G on each strand. And each of our locations or most of our locations have at least 3 pairs of fiber to it, right? So this is pushing it to an extreme. But people are talking about doing this.
Which is a great thing for equipment makers, telecom, compute, but who's going to pay?
That's that's a good question. It's a very good question. Well, we are doing research.
Pay for saving people.
Yes.
Other smart
So there,
in the world, right? that
yes,
experimented like that.
yeah.
Instrumented like, sorry.
Yeah. There are a lot of initiatives, similar initiatives, and people are around the world doing this, right? So
It's just like a slam, right?
yeah, it is. It
And
is.
in your system, do you have a way you mentioned publishing this, broadcasting it to other?
IRB.
That's another thing, but compressing that.
Yeah, so the problem is this privacy issue, right?
Yeah.
So that's, if we can address that, we would love to. Yeah, so we are publishing some recordings that we proved are anonymized enough, so they are available on our website.
No, I was thinking more like a pop, like you mentioned, like a pop cell.
Yeah, so we have with that European startup, with the European startup, we have MQTT, where we are submitting, when we are running the experiments, we are sending them data live through the PubSub infrastructure.
It's that incremental data.
Yes, so we are just sending the bounding boxes of detected objects and speeds and stuff like that. We are not sending the raw video or anything like that.
Right.
So that's all done with the assumption of preserving or reducing requirements and latencies of sending the information. Okay.
All right.
Thank you.